Hi, my name is Steve Enck, and I am a Senior Manager in IoT Consulting at SAS. During this presentation, I'll be discussing a real-time solar farm monitoring project that was deployed using an automated approach called Streaming Analytics Framework. And here's a little background about me. I've been engaged in analytical consulting projects for more than 20 years now. And during the past 8 years, my focus has been on real-time analytics projects where we are able to provide continuous monitoring and analysis. Here's an agenda of what we'll cover today. We'll start by reviewing the business problem and understanding the motivation for the project. Then we'll take a brief look at some of the technical details for the approach. And finally, we'll look at how we actually deployed the project using various SAS products. First, let's provide some background on the business problem. SAS solar farms have a capacity of 2.2 megawatts and generate 3.6 million kilowatt hours per year. That's enough power to operate a standard 15-watt CFL light bulb for 250 million hours. So it's important that we know immediately if the solar farm is not operating at peak efficiency. And we really had two focus areas. One is we wanted to provide real-time monitoring of all assets so that we can ensure that each asset is operating as expected. And we also wanted to be able to quantify the economic impact of the solar farm, both to understand production as well as any shortfall due to outages, maintenance issues, etc. Now, we used the end-to-end capabilities in SAS to deliver the project. Data was processed in real time using event stream processing. Models for each asset were trained using VDMML, managed using Model Manager, and ultimately integrated into the real-time ESP project. Dashboards were developed in Visual Analytics, and ultimately the ESP project was deployed using Event Stream Manager. We accelerated delivery of the project by using Streaming Analytics Framework, which is an automated approach in which the user updates a few simple configuration files, and then all remaining steps, including model training and real-time project build, are performed automatically. So at a high level, this is the approach. Starting at the bottom, we were able to retrieve historical data related to energy production, solar irradiance, and weather from our internal database in a weather service. We used that raw data to build analytic-ready data tables and train models so that we knew the expected energy output from each string in the solar farm, as well as what the aggregate output should be coming from each combiner box, array, and inverter. These models were trained using visual data mining and machine learning and registered and championed in Model Manager. Now, moving to the top section, once we run live, we retrieve real-time data every 5 minutes from the solar farm using an API call, as well as weather data such as cloud cover via a second API call. SAF operates by maintaining a digital twin of the solar farm in memory, and those real-time sensor measurements are used to update that digital twin. At regular time intervals, we output data from that digital twin into analytic-ready tables and score the new records using our trained models, so that we have an actual energy metric and expected energy metric next to each device in the solar farm. And finally, we display that information in VA dashboards and can configure alerts to notify appropriate resources. So now let's look at how the project was actually delivered.
We're going to use Streaming Analytics Framework to accelerate the delivery of our real-time analytics project. So here we are in SAS Studio, and Streaming Analytics Framework is a series of 5 directories where users will input a few configuration files, and ultimately Streaming Analytics Framework will help to train the models as well as build a deployment-ready ESP project. And so here is that project that we are running for the solar farm for our arrays. And we'll spend the balance of our time kind of bouncing back and forth between the Streaming Analytics Framework directories and your final ESP project, so you can see what is needed from a configuration perspective, as well as what is happening in the project once it's built. Just keep in mind that this project in event stream processing is built by the Automation and Streaming Analytics Framework. So all we'll need to do is update a few spreadsheets with our main configurations, and ultimately SAF will build this for us. With Streaming Analytics Framework, users describe the system of assets that they have. Just to give you a quick overview of what these assets or devices are in a solar farm, a string is a small group of adjacent solar panels. Multiple strings connect to a fuse terminal in a combiner box, and the combined output is connected to an inverter. An array is more of a logical grouping of these combiner boxes from a particular area of the solar farm. In our case, we have 5 distinct arrays. And an inverter receives the current from several combiner boxes and converts direct current, or DC electricity, which is what the solar panel generates, to alternating current, or AC, which is what the electrical grid uses. And so the first step in SAF is to build this picture. And in our case, this is our solar farm. We have our solar farm, has 2 inverters. Each of those inverters has arrays. The arrays have combiner boxes, and the combiner boxes have strings. And so in SAF, the configurations that you would do are here in the Connect directory. There is a devices file where we list our devices that we have. And so for our solar farm, we have our solar farm, we have 2 inverters, we have our 5 arrays, and we have these combiner boxes and strings. And the other configuration that you need to do is to map those devices. And so the hierarchy map file, it looks like this. And this is where I would tell SAF that the solar farm is connected to 2 inverters. Inverter A is connected to its arrays, and same for this. And the arrays have their combiner boxes, and the combiner boxes have strings. And so by creating those 2 files, ultimately SAF will give you this picture, so you can confirm that what you've configured is accurate. So the next step is we'd like to get data about each of the devices in our diagram that we've created here. So to configure an input in SAF, you go to the Connect Configure directory and add an input from one of the available options. Now we won't go into the specifics on how to do each one of these, but the key thing is that SAF expects the input to come in a certain format, and so you may need to massage the data coming from your input sources to match that format. So if we go back to our ESP project, we can see that I have 2 sources of data. One coming from the IoT Hub for the solar farm, and another, this is a World Weather Online API. And if I actually go into and see this project running, because here it is, we'll see that the weather API, here's how it responds, and we can see that we get the solar farm. This was the ID for the solar farm in that last page. And this is the different sensors that are available and the daytime and the value of those sensors. And then the solar farm responds similarly. The only thing different here is that this value, right, is not something that we defined in our project, right? The way we drew our picture up, we didn't have a Dev 66. We had inverters and combiner boxes and strings. And so this is kind of how the API thinks of these sensors and these devices, but we need to map it into that picture. And the way you do that in SAF is if you go back into the directories, every time you build a source, you create a sensor map that tells SAF how to think about those sensors in terms of the picture we created. And so here you can see that I have, this is how the API responds, and we can see that the currents all are set. We want to map them to individual strings. And the temperature for this device is the combiner box's temperature. And so this allows us some control where even though our source of data may not think of the data the way we do, right, our digital twin picture, we allow some capability to map that into our picture. And if we come back to our ESP project, we can see that that sensor map is used to add context to each sensor as it arrives. So when we see those individual sensor measurements, we can update our digital twin accordingly. Now, since we added these sensors, now we can come back to our diagram and we can see that each of these assets has sensors associated with them. So this allows us to see what sensors each device has and ultimately what we can use for our outputs later on. So our next step is to transform this simple sensor data, one record per sensor, into more of an analytic-ready data table running live with measures about all the key information needed to understand each device. So in this case, weather, irradiance, information about the inverter, and information about the array. So in SAF, we do this by going to the output configure directory, and we edit a small configuration file where we tell SAF we actually get to design our desired output file. And so here we specify that the device type that we're interested in is array. And by definition, what that'll do is in our ESP project, we'll get a row for every array that we have. So there are our 5 arrays. And if we output every minute, then we'll get a record for those arrays every minute. And then we choose the columns for that data output data set. And here we're going to pull the arrays current, and that's an easy measure to pull because we're looking at arrays. But then you'll see some of the other options here where we're pulling the inverter's voltage and the weather from the solar farm and irradiance from the solar farm. And if so you go back to our picture of our system, the reason we can specify this so simply is because we already know our digital twin. We know how the devices are connected. So the logic inside SAF builds what's needed to pull that information. Now, it's worth noting here that while we've kept things simple for this demo, there are actually quite a few options you could use. Things like asking for values back in time, like what was a value an hour ago, or aggregating measures like summing across the strings for a given array or inverter. Those are all possible in SAF, but that would be a topic for a future presentation. So now we've configured everything that we need for SAF, so we can go ahead and build our ESP project. So we'll specify our site as solar farm, our device type is array, we'll output every 60 seconds, and then we'll build. And our build has completed, and we take a look at the log and we see that SAF has done a variety of things to build our project, and we can go view our project in the production code directory that gets created. And so here is the array directory. And you can see it has some various lookup tables, and it creates 2 projects, one to run real time, which is the one we're watching, and the other one where we can replay data from a historical data set. So now if we bring that ESP project into ESP Studio, then we would have all of the windows shown here, except we wouldn't have those models down at the bottom. And so the way we're going to get to those models is we are going to use the historical project to replay that historical data. And now we'll have a year or 2 years of data that we can use to train our models. So we've done that already. And here is that data in a SAS data set. We had mentioned in the opening that we wanted to know how our actual energy use compares to the expected energy use. So we'd like to train models to predict the current or aggregate current associated with each part of the solar farm based on factors such as cloud cover and solar irradiance. A typical approach we use is to choose a handful of devices and then spend a fair bit of time testing out models in Model Studio. Once that first model is developed, we can allow SAF to fit models for all of the remaining devices by following a similar approach. We'll analyze inverter A here. So we have all of our variables in here, and we have built our pipeline, and we tried a few different models to see. And if we go in and look at some of the results, we can see that the key predictors were irradiance, temperature, the irradiance cubed, humidity, and irradiance squared. And so then once we've done this for one model and we have an idea of what are the key predictors, we can go over to SAF, and there is a location where we can provide our inputs. And so that input file is very simple. And here it is for our values. We were looking at arrays. So we have our target as the current, and we have a radiance squared and cubed, the temperature and humidity, and the average temperature of the array. And so this is all we need to specify. And then we can tell SAF to fit our models, and we have to give it a training period. So this is August 2020 through December 2020. And the test period is the first 6 months or so of 2021. And we hit run, and that will train all of our models. And actually, as it trains them, it will also register them into Model Manager. So I can see them here, and if I went into any one, I could see the all the different artifacts, but I could also see the history. And so I can see when I championed a new model. Now that we have all of our models trained and registered with Model Manager, we can come back to the SAF Build UI and build our project with models. We'll request to get the available models from Model Manager. And we can see that we have a different model for each of our arrays, predicting the expected current for that array. So we'll select all and deploy. And we can look at the log, and we'll see that in addition to building the project, we can see it's retrieved those models from Model Manager. So if we come back into Event Stream Processing Studio, we could bring that project into ESP Studio, and we would have exactly the project we've been working on throughout this presentation. And now that I have my models integrated into my project, I will have predictions flowing in. So I have one record for each array, updating every 60 seconds. And in addition to the weather, the irradiance, the inverter, and current metrics, now I have predicted and standard error metrics. And so that's what I can use to develop my efficiency metric on the Visual Analytics dashboards later on. So now that I have my project finalized, it is ready to be deployed into production. So I can choose to version that project, and I can give it a brief comment. And then I can go over to Event Stream Manager and deploy it. And you can see already over here, I've created a deployment, and I can see all of my different solar farm projects for the array, combiner box, inverter, solar farm, and string. So I've created a different project for each. And I can see that they're all running properly. They have a green check mark. And if I wanted to go into the health of each one, I could see that all of the proper things appear. Things are running that should be, and I can even see data rates and things like that. I'll close as I click through a few of the VA screens that were made possible by having this project running live. So if we looked at the main gauge for production at the solar farm, we can see that inverter A is producing 100% of expected output based on those machine learning models. And if we delve down, we can see that each of the arrays is doing the same. If we look at the efficiency charts, we can see detail about each of the combiner boxes, and all are operating at 100% except one is at 98%. And finally, if we wanted to see even more detail about the machine learning model results, we could see that the current right now, the actual current is about 109. The expected current was about 108 based on the machine learning model that takes into account weather. And then we could also see that array A2 is performing a little bit above expected, and array A4 as well. So this allows us to always be monitoring and comparing actual to expected. And from an overall perspective, we created this exploration dashboard where business users could go in and see that over some period of time, how did the solar farm perform? So you can see that from January to the end of July, we expected production of about 644,000 kilowatt hours, and we actually generated about 625,000. So quite good. And then if you were to delve in by month, you could see how each of the months compared over time, and similar for the other device types.
This concludes today's demo. If you have any questions or comments, please feel free to contact me at the email address on this slide. Thanks for watching.